Welcome to the afternoon session and the session on multivariate public key cryptography. And so here we have Jeremy Vates from the University of Louisville, which was collaborated work with Ryann Cartor, Ryann Gipson, and Daniel Smith-Toney. Let's welcome Jeremy.
Thank you very much. So my colleagues and I started doing some work on the differential security of the HFEv minus signature primitive. And before this talk starts, I would ask for forgiveness for the misspellings that may occur. My math ability, I promise, far supersedes my ability to spell. All right, so before we get started, I would like to talk about some just simple motivation for analyzing the differential when we're looking at our different schemes for multivariate. Many attacks that are done on some very famous schemes can be seen through the differential perspective. And some big examples are Patarin's attack on C star, the attack on S flash, and the attack by Kipnis and Shamir on the oil and vinegar scheme. Some previous work that has been done in analyzing the differential has been done by Polner and Dr. Smith-Toney on C star and PC star, as well as Taylor Daniels and Dr. Smith-Toney on the HFE and HFE minus schemes. So in this presentation, I'm going to give some basic scheme structure and some basic definitions, and then we'll move on to analyzing the differential symmetry of HFEv, as well as the differential invariant structure within HFEv, and then finally just comment on some future work and some conclusions. So let's start with the basic structure for HFEv. We take an n degree extension of FQ for our extension field K, and then we have the basic definition of our core map, where we have our oil vinegars in this monomial, our mixing variables within our center term, and then our vinegar variables at the very end. Next, we take the butterfly construction of our core map in order to hide some basic structure. So giving the basic definition of the discrete differential on our core map is the following equation given below. Essentially, it's just a differential, it's just a normalized difference operator on our core map. And in this paper, we analyze from the perspective of a differential adversary, and we define this person as someone who is attempting to gain structural information about an unknown field map by discovering properties from the map's discrete differential. So these properties that the discrete differential opponent or adversary will try to analyze. The first one is a linear map M that satisfies this differential symmetric equation. Trying to find a linear map M that satisfies that in a way to gain some structural information about our core map, thus giving them the ability to undermine our scheme. Another thing they'll be able to analyze are two subspaces, V and W, where the dimension of the subspaces are added up to be greater than or equal to n, where n is the number of variables, such that when you calculate the differential, the discrete differential at the vectors within V and W, it's equal to 0. So finally, let's go ahead and take a look at our core map in a slightly different perspective. Here we look at it in a bivariate scenario. A small comment on this. Our x and y represent our oil and vinegar variables respectively. In this case, our x is represented by an n by 1 vector representation, and as well as with our y. However, our vinegar variables normally are not the same number as the oil. Thus, in order to look at it from this perspective, we concatenate as many zeros as is necessary in order for them to be an n by 1 dimensional vector. And then below this, we just give a basic definition or perspective when we calculate the differential on our core map with this bivariate structure. So let's go ahead and start analyzing the differential symmetry of our core map. Our goal is to prevent our adversary from having any possibility of an M, which is a K to K linear map, that satisfies that differential symmetric equation. So like I mentioned before, we use this representation for our oil and vinegar variables, x and y, where it is n by 1 dimensional vector for x and for y respectively, where we take x and then to sequential powers of q. This allows us to look at our differential symmetry equation in a matrix representation, and it allows us to just get our hands on what is actually happening. So in doing so, we can always take a look at our FQ linear map with this given representation, which is an n by n matrix in this representation, where we have the first row is given with just variables m0 through m to the n minus 1. And then when you go down to the next row, all you do is you shift your entries to the right 1 from the previous row and then take them to sequential powers of q. This was the M representation that was used in analyzing the HFE and HFE minus structural from Dr. Smith-Toney and Taylor-Daniels. However, when we extended it to the HFEv structure, we had to do a slight adaptation. Since we have this bivariate structure, this 2n by 2n, we had to adapt our M matrix from the n by n representation to where we have these n by n block matrices, M00, M01, M10, and M11 for M bar, where each M matrix has that representation shown above. So looking at our differential symmetric equation, we wanted to get a matrix representation of the equation. So we just do some quick reductions using the basic properties of the differential, and we get the following representation of our differential symmetric equation with matrix representation. In our analysis of the differential symmetry, we focus solely on this equation and trying to prove that no non-trivial solutions M and lambda M that satisfy the equation. So here is where the real fun came in our paper. It was analyzing this pictorial representation of our symmetric equation, point 2. And this pictorial representation was just a really easy way of analyzing a very large matrix systems of equations. I tried to do some color coding in order to make it very clear where the non-zero information for each line is coming from. I hope it's okay to see on this projection. But we have horizontal and vertical lines as well as diagonal. And the question is, well, what are these lines representing? These lines are representing possible non-zero information within our symmetric equation. So in point 2, our symmetric equation, the left-hand side is represented by horizontal and vertical lines. And those lines are generated, for example, the red lines are generated from the alpha monomials within our core map, and they extend horizontally across the entire image. And then our beta terms from our mixing variables is where you get the blue horizontal and vertical lines, and then the green for the gamma monomials respectively. The right-hand side of the equation, the lambda m dp, is represented by the 45-degree angle diagonal lines, and this is where you have non-zero information on the right-hand side of our equation. So in our analysis, we were just trying to determine where we have indices of m and attempting to prove that no non-trivial solution existed. So in our analysis, we are really trying to look for information that can be seen right here, for example. It's where you have a horizontal line or a vertical line that has no intersections. And the information that this line represents is where, on this red line, for example, you would have your coefficient alpha times some index of m raised to some power of q. And since it does not have any intersection with the diagonal line, that indicates it's equal to 0 within the matrix representation of your differential symmetric equation. From there, you can deduce that that index of m within your m matrix is equal to 0. That gives you information that you can use to further analyze this this linear map that the differential adversary is trying to find to exploit some structural information about your core map. So what our algorithm does that we generated is it looks at all possible non-zero information. So the non-intersections here give you information where certain indices of m is equal to 0. Now where you get possible non-zero information is when you have horizontal and vertical lines intersecting, as well as horizontal lines and vertical lines intersecting diagonal lines. This gives you possible non-zero information. So we generated an algorithm that basically looks at the space of indices, is what we call this image, and it generates a set for all possible non-zero indices of m. So it goes per horizontal or vertical line, per alpha, beta, gamma monomial, and looks at anywhere possibly that you might have non-zero information on that line. It stores that information and moves on to the next horizontal and vertical line to successively store that information. And then it cross-references all such sets. When it does that, it will return to you the only element within the M matrix that is possibly non-zero. In doing so, we are hoping to show that the only possible non-zero indice of M is M0. And M0, that indice represents a diagonal structure matrix for our M. So we give some following restrictions to our HFEv core map in order to allow our algorithm to actually analyze the information. Without these restrictions, it becomes much more complicated to analyze what is happening. These restrictions on our core map are let no power of q be repeated among the exponents of f, make the differences of powers of q unique, and then restrict your choices of exponents to triangle numbers within suggested parameters provided by Dr. Jintai Ding with his GUI structure for HFEv minus. And I'll give some slight motivation behind those choices of restrictions. When you have a repetition of powers, the issue that does occur is you'll have an overlapping on horizontal and vertical lines. That overlapping, it just destroys the places where you're able to deduce that you have information of an m indice equal to 0. So when you have that overlapping, it doesn't allow us to really analyze what's going on. It's too much to work with, so we put that restriction on there. The other one is the uniqueness of differences among the exponents. That is solely for the purpose of making sure our diagonal lines do not have any overlap as well. When you have the repetition of differences, you end up having overlappings on your diagonal lines, again, making it even more difficult to analyze the positions that are possibly non-zero. And then the final point that we tried to restrict the choice of exponents to triangled numbers was solely for the purpose with our by-hand analysis of this system before we defected to using an algorithm, is that we saw this repetition of uniqueness of differences being necessary for m0 being the only index of m possibly being non-zero. So within our choices of triangle numbers, and then we ran the algorithm, it produced the exact result that we expected. This choice of restricting your exponents to triangle numbers isn't necessarily firm proof. You may not need it. You can still run the algorithm without this restriction on your HFEv core map, and you may still be able to provide, or given the result, that your system is still secure against a differential adversary using the differential symmetric equation. So what happens in this scheme when you get m0 being the only non-zero piece of information? When you analyze it from the HFE perspective that was done by Taylor Daniels and Dr. Smith-Toney, you ended up getting M to be a diagonal matrix. And that was fantastic because it resulted with basically M being a multiplication map, where it was you had an element times the diagonal matrix being from the base field FQ. And that was just a trivial differential symmetry. It didn't reveal any extra structural information about your core map. However, when we extended it to HFEv, we no longer got just a nice basic structure of a diagonal matrix. Actually, since we restrict ourselves to analyzing M00, M01, M10, M11 block matrices at a given time, you end up with a block diagonal matrix. And it's not as clear that this actually is a trivial differential symmetry when you have the coefficients C and D being from the base field. So I just showed here real quick is just doing a basic calculation using the differential with M bar with that structure. And you can see really quickly, just using basic properties of the differential, that this is a trivial differential symmetry. Every core map is going to have this kind of structure, so it doesn't reveal any unique structure of your core map. It doesn't give the adversary anything to be able to take advantage of in trying to break your scheme. So we were able to develop an algorithm that can easily be placed within a random key generation that can check to see if your core map is secure provably against a differential symmetric attack. So that was fantastic. Let's go ahead and move on to the HFEv minus and see the slight adaptation that had to be had when you put on the minus modifier. So when you put on the minus modifier onto your core map for HFEv, what ends up resulting within our pictorial representation of our differential symmetric equation is you actually generate equal to the number of lines that the number of equations that you remove with your minus modifier. So this pictorial representation shows two equations being removed from your public key. In doing so, at every place that you originally had a line in the HFEv core map, you have two lines being generated, one apart from the original line. So this actually made it even easier to analyze. We had more information to deal with where we knew specific indices of m that would be equal to 0. And even though it did generate some extra locations for possible non-zero information, it generated even more spaces where we are guaranteed that that indice of m is equal to 0. So in our algorithm, we just need a slight adaptation to deal with the minus modifier. We actually call HFEv as a subroutine, that exact analysis we did with HFEv. And then we append to that algorithm all the extra sets of possible non-zero entries in M. And that's the pictorial representation showed two equations being removed. So for every place the HFEv called it, you would do two extra sets for the extra two lines that were generated in our image. So even more information to work with. And then after that, you intersect all such sets, and it will return the only index within M that is possibly non-zero. So in result, we were able to give a very, very efficient algorithm that is able to use within a random key generation that can provably or give provable security against a differential adversary. Something that should be noted here is that in proving security against a differential adversary, you could do that very simply by just solving a system of linear equations. That's all we're doing here is we're looking at a system of linear equations and solving for them. However, that's quite cost effective within a random key generation algorithm. It takes too much time, too much resource. Our algorithm is very, very minimal in resources and necessary and very, very fast. So it's a much better alternative than trying to just solve these systems of equations linearly with our known techniques. So now that we analyzed the differential symmetry, let's move on to the differential invariant. So given a basic definition of the differential invariant, we have our F being our core map. A differential invariant of F is a subspace V within your extension field with the property that there is a subspace W within the extension field such that the dimension of W is less than or equal to the dimension of V. And then for all A within the span of FQ DFI, AV is contained within W. And just a small clarification that DFI represents the differential being calculated at every public equation F sub I. Then we can give a definition for VPerp. This is not the standard definition that we use for VPerp. It's slightly altered to fit our needs within this analysis. And VPerp is equal to, assuming that we have a differential invariant V, it's all X within the extension field, such that when you calculate the inner product between X and AV, remember A comes from the span of DFQ, the span of FQ DFI, it's equal to 0 for all V and V and for all A within that span. So some small prepositions that we needed before we go ahead and get into some of the theorems that were proven within our paper is one is that we have a, suppose that V is a subspace of K. If M is from K to V and M perp is from K to V perp, then for all X and Y within FQN, the differential calculated at M perp Y and MX is equal to 0. Or equivalently, you have that following expression for the differential. Using that, along with this following proposition from basic linear algebra, if you have two matrices, A and B, that are n by n matrices, then the ranks of them are equal to each other if and only if there exists possibly non-singular matrices C and D, such that A is equal to CVD. Using these two propositions together, we can write M perp in the following form, where M perp is equal to SMT, where S is possibly singular and T non-singular. So we get to the first theorem proven in our paper, and again we start with the HFEv system in order to get our feet wet before moving to the HFEv minus. So here we start with K being a degree and extension of the finite field FQ. F is our HFEv core map. With high probability, we have proven that F has no non-trivial differential invariant structure. And I'm just giving a quick proof outline because the proof is quite complex trying to shove into a slideshow, and I highly recommend to go to our paper to see the exact details. So the proof started with, we calculate the differential of our core map using, again, the SMT representation that mentioned in the previous slide, and MT multiplied by AB transpose. In contrast with the analysis done on the HFE, our monomials are not necessarily independent, so we had to slightly adapt our analysis to compensate for that. So our representation for the differential, we use generators of HIVv. We evaluate the previously mentioned those generators, differential modulo IV, and the resulting monomials that we get are linearly independent. So continuing to prove, due to the independence of the resulting monomials, we get the following equality, where L is an n by 2 matrix with entries in FQ. We expect L to have high rank with probability more than 1 minus q to the minus n. Thus, we get the dimension of the intersections of the null sets of each L is 0 with probability at least 1 minus 2 q to the minus n. The condition for the above equation to be satisfied is that S sends V to the intersection of null spaces for each such L. Thus, S is with high probability the 0 map on V, and so V perp is equal to the set containing 0. This implies the following inequality, which results within a contradiction. So we have proven with probability greater than 1 minus 2 q to the minus n, F has no non-trivial differential invariant. So now we've proven it for the HFEv system. Let's go ahead and move on to the HFEv minus. We have F being an HFEv core map, and then we do the pi being a linear projection. That's our minus modifier. With high probability, pi composed with F has no non-trivial differential invariant structure. This proof is very, very similar with the outline that I just mentioned with HFEv. There's a slight difference in the probabilities, and then one small thing that should be noted is that since the condition of being a differential invariant is a condition on the span of the public differential forms, under this projection, the condition is weaker, so it's even easier to satisfy. So some final thoughts. We just finished up with analyzing the differential symmetry and the differential invariant. Some small things about the differential symmetry. We placed quite a few restrictions within our core map, and it's a very logical question to ask: have we restricted that too much? Do we have enough entropy within our public key? And the answer is yes. We still have plenty of entropy left over, even with some of the given restrictions. And again, this algorithm that we produced in order to analyze the differential symmetry, the first two conditions I would highly recommend to use. Otherwise, the algorithm will take much more time with those intersections overlapping of horizontal and vertical lines. But the third one, using the triangle numbers, may not be necessary. You may be able to find ones that are secure against a differential symmetry without that restriction. Second, along with careful analysis of the Q rank and the degree of regularity already present within the literature, we have shown that HFEv- is very, very secure against all attack methods known. So thus, in order for HFEv- to be broken, it's going to have to be by some fundamentally new technique. So thank you very much for your attention. I'll be happy to answer any questions that you have.
Any questions from the audience?
Can you use this technique to analyze other maps? For example, PS Flash.
Yes, I don't see there'd be any reason why. We've done this analysis with C star, PC star, HFE, HFE-, HFEv, HFEv-, and the analysis has been extended quite naturally with very small adaptations to our analysis. So future work going forward, again, our goal is to just give some kind of provable security standards that we can have within on these crypto systems. So I would see no reason why the analysis wouldn't extend quite naturally.
I mean, P flash is C star minus, so I mean that's included in his.
Exactly.
Okay. So I guess I have a question. Sure. So did you program like your the key generation that you have in C, and so to have some like speed comparisons with previous?
We never tested actually using the algorithm within a key generation. Actually, we took specific examples of core maps that you would use, and then ran the algorithm within those specific examples. So there is no reason to suggest why using the multiple different cases that you can have on the random key generation would take more time, as long as you stay within the restrictions of unique powers of Q and then the uniqueness of differences amongst the powers of Q. Those are the main things that will cause the algorithm to run much slower, because you're taking intersections of much larger sets. By having that overlapping, you end up having much more possible locations of possibly non-zero information. Thus, you're taking intersections of larger and larger sets, which would take more and more time. So as long as you stick to restrictions 1 and 2, there is no reason why the algorithm would run any slower.
Okay.
Sorry. So I'm really confused with the theory you just said. No symmetry, whatever. You claim in general for all the HFEv. I mean, we know the impact of A and B and the degree of HFEv. I mean, in the case of mass multi-mining, we know you have a differentiation. So your statement has nothing to do with the size of A and B and degree, or I'm a little bit confused.
I think I'm confused on the question that you're asking.
The probability, you have a probability statement, right? But the probability has nothing to do with n, which is the degree d, and then the number of minus and the number of vinegar variable.
Right.
That's a bit strange to me. Is that right, or I'm saying something?
I think that question would be best talked about independently. I myself didn't do the analysis on the probabilities. That was my colleague, Dr. Smith-Tone. So we'd be happy to answer that question.
Okay.
Thank you for your question.
Okay. So thanks to the speaker again, and.